Hi, in this video we will study properties of orthogonal complement, and we will see that what is the orthogonal complement of row space and column space of a matrix. Well, let me recall what is the orthogonal complement. So we assuming that W is a subspace of Rn, then we define W perp or orthogonal complement of W to be all vectors in Rn such that v dot W is equal to 0 for all vectors W in the subspace W, capital W. And we saw that and we know that first thing, the easy case, we know that zero vector is in W perp. But we can show even more that if a vector is in W perp, then any scalar multiple of that is going to be in W perp too. So in other words, W perp is closed under the scalar multiplication. Wow. Well, if V is in W perp, that means that V dot W is 0 for all vectors W in the subspace W. Now, if you multiply this whole thing by C, which we know, by the way, is C times 0, and that is going to be 0, this you can write it as CV dot W, and here's for all vectors W in W. So what we showed is that if this is true, this CV dot W is also 0 for all W's in W. That means that actually CV is in W perp. We can also go further, so let me put a box there. We can go even further. If we have two vectors, v1 and v2 in W perp, then v1 plus v2 are in or is in W perp. In other words, W perp is closed under vector addition. And how does that work? Well, if v1 and v2 are in W perp, that means that v1 dot W is equal to 0, v2 dot W is equal to 0. Now we want to show that v1 plus v2 dot all the vectors in W is going to be equal to 0. We know that dot product can be expanded over the vector addition. So this is this. And since v1 and v2 are in W perp, this is going to be 0 plus 0 and 0. This will be true for all vectors in the subspace W. And well, that means that right away v1 plus v2 is in W perp. Well, if I put all these three together, what I have is, this is the fact one, that W perp is a subspace. So you start with a subspace, find its orthogonal complement, it is going to be another subspace. Very nice. Well, the second thing that I want to discuss is that, well, usually we don't have the subspaces given to us as this description of very general thing. What we have is that usually we have a subspace given as span of some vectors, v1 up to vk. Now you have w perp on one side, which is all the vectors in Rn, which is orthogonal to all the vectors in the span of v1 to vk. Also, you can form this set also. We are considering all vectors in Rn which are perpendicular or orthogonal only to v1, v2, v3, and up to vk. So this is true for all I from 1 to k. So I'm not assuming it is orthogonal to all the vectors of w, but just this set of vectors that span the whole space w. Well, obviously, if a vector is here, that means that it is orthogonal to all the sets of w, and in particular, it will be orthogonal to v1, v2, v3 up to vk, because v1 to vk's are in w, so that means that this is true. We want to say more. We want to say that these two are equal indeed. It means that if something is, if v dot vi's are 0, then any linear combinations of these guys you take, c1, v1, and cn, ck, vk, this is going to be also 0, because it will be c1 v dot v1 plus c2 v dot v2, and this will go up to ck v dot vk. And since each one of these guys are 0, so this is 0, this is 0, this is 0, this will be equal to 0. So what we showed is that if something is orthogonal to all vi's, then v is orthogonal to all linear combinations of v1 up to vk. Well, what does this mean? This means all the linear combinations of v1 to vk are exactly the whole set span of v1 to vn, which is to all vectors in w. And that means that v is indeed in w perp. So I'm just, I am going to write this as these two are equal. So this is fact 2. What does it say? It says that if you have a generating set, a set that spans the whole subspace, you don't need to check all the vectors in this subspace. You just need to check all the vectors which are orthogonal to these spanning set. We will use that, and we will see something interesting in case of matrices. Remember that for any matrix, recall that for a matrix A, which is m by n, we assigned at least two subspaces, rho subspace and a column subspace. Now we want to see what are the orthogonal complements of these guys. Okay. Well, let's assume that V is in row space of a perp. That means that V is orthogonal to all vectors in row space of A. But we know that row space of A is span of rows of A. So let me write row 1 up to how many rows we have? M rows we have. Yes, here. So these are spans of those ones. And being there, that means that V is orthogonal. Actually, this is if I only orthogonal to row 1, row 2, up to row M. Well, if I write this in dot product form, I will write the other way around. R1 dot V is going to be 0, R2 dot V is going to be 0, and Rm dot V is going to be 0. Very nice. But here, this is the same thing as we have row 1 here, row 2 here, up to row M here. And then we multiply it by V as a column vector. So row 1 to V is going to give us 0. Row 2 is going to give us 0. Row 3 gives us 0. So that means that V, A dot V is equal to 0. But we know such a thing has a name. So V is in null space of A. Well, and this is if and only if. What we showed here is that actually, so this is fact 3, and we will use this very strongly, that that a row space of a vector, you find the orthogonal complement of that. This is the same thing as null space of A. So you just need to find the complement, all vectors which AV is equal to 0. Solve it. Solve the homogeneous system with the coefficient matrix A. How about column space? Well, the column space now is easy because column space of A we know is the same thing as row space of A transpose. Now that you find the orthogonal complement of that, you know that this is going to be null space of A transpose, because row space we just had as fact 3, that row space complement is null of that matrix, and that is the fact 4, that column space, if you want to find the orthogonal complement of column space, you need to first find the transpose of the matrix and then find the null space of that matrix. So as you see, for a matrix, now we have 1, 2, 3, 4 subspaces. These subspaces sometimes are called fundamental subspaces of a matrix. So let me just write the definition here. So the subspaces row space, column space, null space of A, and null space of A transpose are called the fundamental subspaces of matrix A. And we saw that what is the relation. We will use these facts, especially fact 3 and 4, to find orthogonal complements of a set, a subspace generated by some vector.